Welcome to Chapter 5, Looping. By the end of this chapter, you'll understand loop concepts, creating loop logic, using loop control variables effectively, and avoiding common loop mistakes, differentiate loop types, like for, while, and post-test loops, recognize characteristics of structured loops, and explore loop applications like data validation, accumulation, and automation. Looping reduces code redundancy, speeds up development and debugging, and handles repetitive tasks with far fewer errors than writing the same logic out manually. Every loop relies on a loop control variable, initialized, tested, and updated to manage its behavior. There are two control types. Definite loops use counters for a fixed number of iterations. You know exactly how many times it'll run, while indefinite loops use sentinel values for flexible iterations, where you don't know in advance how many times it'll run. Definite loops have predetermined iterations, like counter-controlled loops, with the loop control variable set before the loop begins and adjusted each iteration. Indefinite loops have user-defined iterations, like sentinel-controlled loops, with input primed before entering the loop and prompted again at the end of each pass to update the sentinel. Post-test loops execute the loop body at least once before ever checking the condition. That's a do-while loop. And nested loops are loops within loops, handling combinations of data. Every definite loop follows three steps. Initialize the loop control variable, assigning it a starting value that determines where the loop begins. Test it, checking a condition before each iteration that decides whether the loop continues or exits when it becomes false. And update it each iteration, moving logically closer to that exit condition. Skip this step, and you risk an infinite loop. Here in Python, I starts at 0, tests while I is less than 10, prints it, then increments by 1 each pass. A definite loop has known iterations. It runs a fixed number of times, determined before the loop even starts. It's typically implemented with a for loop, since for loops are built to iterate over a sequence or range. And because the iteration count is predefined, a definite loop always terminates after that count completes, which meaningfully reduces the risk of ever running infinitely. Definite loops are great for generating a sequence of numbers, printing a multiplication table, calculating squares, iterating over a fixed dataset, or processing every element in a list or array when you already know how many items there are. Here, a for loop counts from 1 to 10, printing each multiple of 5 along the way, in both Python's range-based syntax and C++'s classic for loop structure. You can build a definite loop with a while statement too, as long as you handle initialize test update yourself. In Java, C++, and Python here, I starts at 0, initialize. The loop tests whether I is less than 5, printing I each time, then increments I by 1, update. Same 3 steps as any definite loop, just written with while instead of for. A for loop is the more natural fit for definite iteration, since it packs initialize, test, and update into a single line of its header, for int I equals 0, I less than 5, I++ in Java and C++, or Python's for I in range 5, which handles all 3 steps automatically behind the scenes. Same logic as the while version, just far more compact. Indefinite loops follow a different pattern. Prime, test, prompt. Priming sets up the initial state or input before the loop's condition is ever evaluated. Testing checks, at the start of every iteration, whether the loop should keep going or stop. And prompting updates the control variable from inside the loop itself, so the exit condition eventually gets met instead of running forever. Here in Python, a while true loop keeps asking for input, breaking only when the user types Q. An indefinite loop keeps running until a specified condition is met, one that might not be knowable in advance, since it often depends on user input, external data, or some other dynamic condition. These are typically built with while or do-while loops, since both check a condition before or after running the loop body. The real risk: if the exit condition isn't carefully defined, or the control variable never updates correctly, the loop can run forever, causing serious performance issues or crashes. Priming is the process of setting up the loop control variable before a while loop ever begins. Initialize it, test it to see if the loop should even start, then modify it inside the loop to guarantee it eventually terminates. The purpose: making sure the loop runs efficiently and avoids 2 classic mistakes, running infinitely or never running at all because the initial test already fails. Here in C++, the program primes with an initial input, then loops, as long as the user hasn't typed exit. Priming matters for 3 reasons. It ensures the loop condition evaluates correctly on the very first pass, since the variable already has a valid starting value before testing begins. It avoids skipping necessary logic, since the first input or setup happens outside the loop, rather than being missed entirely. And it keeps the loop's logic clean, creating a clear separation between one-time setup and the repeating iteration itself. Here in C++, priming reads an initial choice, then the loop keeps prompting until the user enters Q or Q. Indefinite loops shine whenever you're waiting on user input, common in menu-driven or interactive programs, or monitoring a system or sensor that needs to keep running until some real-time condition occurs. A sentinel value is the signal that tells the loop to stop. Here in Python, typing Q breaks the loop. In C++, entering -1 acts as the sentinel that ends the number entry loop and prints a closing message. Here's the full prime test prompt pattern as actual Java code, using a scanner to read input. The program primes by reading an initial choice, tests whether it equals Q to decide if the loop continues, and prompts for a new choice with each pass, continuing until the user finally enters Q to quit. And here's that same prime test prompt pattern in C++. Prime with an initial read into choice, test whether it's not equal to Q or Q, and prompt for a new value inside the loop body each time through identical logic to the Java version, just with C++ string comparison syntax. Here's the same pattern one more time in Python. Prime by reading the first choice, test with a while loop checking it's not Q, and prompt for a new choice inside the loop on every pass. The exact same three-step structure, working identically across all three languages. Loops power three common tasks. Data validation uses defensive programming to validate a value's type, range, and consistency before trusting it. Totals and accumulations use an accumulator variable, always initialized before the loop begins, to sum up values as the loop runs. And automating processes often means reprompting a user for invalid input, with sensible limits, so they don't get stuck repeating forever. Here in Java, a do-while loop accumulates entered numbers into a running total until the user enters 0. In a nested loop, an outer loop controls how many times an inner loop runs, and that inner loop completes fully on every single pass of the outer one, creating a repeated process across two dimensions, like rows and columns in a grid. Nested loops are the go-to tool for 2D data structures, grids, tables, matrices, coordinates, generating combinations, or building patterns. If you're new to them, understand the inner loop on its own first, test with small ranges like a 3x3 grid, and print intermediate output so you can actually watch the execution order unfold. Here's a nested loop as actual code, in Java, C++, and Python. The outer loop counts through 4 rows, and for each row, the inner loop counts through all 4 columns, printing every row-column coordinate pair along the way. The result is a clean 4x4 grid of coordinates, exactly the kind of 2D pattern nested loops are built for. Before next class, convert an everyday repetitive task into pseudocode and a flowchart. Something like checking a shopping list for completion, or repeatedly asking for a correct PIN number until it's entered right. Bring it to class for review, and be ready to walk through how your loop's prime, test, and prompt steps map onto the real-world task you picked.